Hello, and it's week 3 of process control. This week we're going to look at second order and higher order systems. The first mini lecture now is going to look at second order systems, and then we will build on that in the other ones. Okay, so previously we saw that many systems could be described as first order. We could analyze their behavior, write down the equations, and find that this generic form of first order linear ODE described their behavior, where tau and kp are parameters that describe it. Tau is a process time constant, kp is a steady state gain. So for any particular system, tau and kp will be different and dependent on different parameters of that system, but the parameters of the system can be grouped in different ways to form these two values, and these two values will describe the response of the system. That can be represented as this. It's a transfer function, which is what you get when you turn this into the Laplace S space. And we saw that for this type of system there was a generic response which looked like this. So if you knew what the equation was and you knew what the parameters were to calculate tau and kp, you could see that the response would look like this. This is the response to a step change input, and after the step change the process responds by increasing and approaching kp, that's the steady state gain, and that after this is t divided by tau, so after one time constant period you would be 63% of the way towards that steady state gain. So maybe you can predict that, or alternatively you might have a system you don't know what the parameters are that describe it, but you can do an experiment and take some measurements, and then you could plot out the results, which will be of this form, and then you can use the results to find these values. You could find the value that this tends towards, and that would give you kp, and then you could take 63% of that and find the time at which that occurs, and that would give you tau. So you can use this characterization both ways. And we fast forward, we're not going to derive this whole equation for a particular system, we're just going to tell you that there are such things as second order systems too. A second order system is described by a second order linear ordinary differential equation. So second order means it's got a dy by dt squared term in it, and linear means that all of the terms of y are linear. There's no y squared or y to any other power, they're all to the power 1. The equation is linear in y, so it doesn't mean that it has to be linear in t. So this function f of t could be t squared or a sinusoidal function. What matters is it's linear in y. And it's an ordinary differential equation, which means we've got the total differentials here. It's not a partial differential equation. And we've identified tau, zeta and kp as process parameters. Tau and kp we've met before in the first order case, and the new one is zeta, a damping factor. So we'll see what the effect of zeta is in a moment. Let's expand the lecture notes that you've got and consider the points in here. So a second order system, as we've said, it's one that's described by the solution of a second order differential equation, and we find them in a few different, three different situations really. One is in situations where you have multi-capacity processes, so you have two or more first order systems in series. So if you have one thing following another thing, even if each one individually is first order, that can give rise to second order or higher order systems. Some are inherently second or higher order in and of themselves, so a lot of fluid or mechanical processes will be like that. Or thirdly, we can create a second order system when we introduce a controller. So you might have a first order system, but when we introduce a controller, then that makes the combination into second order. So this will occur in a number of different situations. So some specific examples: things that are inherently second order. So we've got a manometer, pneumatic valves, differential pressure transducers. These are all things that have fluids moving within them. So there's inertia and there's acceleration taking place. In different branches of engineering you'll find exactly the same types of problems. In electrical engineering, if you have a circuit which has capacitors and resistors in, the combination of those gives rise to second order equations. And in mechanical engineering, if you have a spring and a dashpot, then those systems give rise to second order equations too. So these are very common processes across all branches of engineering. As we said, we can also have a combination of first order systems. So if we just have one of our first order systems followed by another, that will make it a second order. We'll see some examples of that in the future mini lectures this week. And then thirdly, things constructed by humans. When you have a process control system, the act of adding a controller will introduce can introduce second order effects. So we'll see that later on in the lecture series. Okay, so before we move on to looking at the Laplace transform, I have a demonstration for you. Here we go. So here is Halloween week. There we go. So Halloween week, this is my kids. I stole my kids' hairband. There it is. Ooh. And this is a second order system. If you look at it, give it a twang, it responds to a perturbation by oscillating, but then that decays and tends towards a steady state value. So this is a system that's got storage of energy in the spring, and then it's got dissipation of the energy as it moves, and the energy gets dissipated through the spring and through the air, movement against the air. And this is a second order system. So you could try and analyze that to work out what's happening at a mechanical level, or you could just look at the response and you can learn something about the system by looking at the response to an input. So we'll look at that again a little later. We want to characterize our system. Here we go, next page. So this was the second order equation that we wrote with our terms in, and we want to apply the Laplace transform method to this as well. So that's going to check that we can do the Laplace transform. So we take the Laplace transform of each of the elements, see what happens. So the first thing to say is we've assumed already that we're looking at the deviation variable in this case. So y is the deviation from steady state, and that enables us to make the same simplifications we made before. So to find the second order differential, you have s squared times the Laplace transform of y minus s times the initial value minus the gradient at time 0. Well, we're looking at the deviation from steady state, so at time 0 there is no deviation because it's at steady state, so that's 0. And at time 0 it's at steady state, so the derivative of y is going to be 0 as well. That's a nice simplification again, so we just have this term here. Likewise, when we take the first order derivative, it's s times Laplace transform of y, and the initial value is 0 again. Laplace transform of y and Laplace transform of f. And so that works out nicely. We can rearrange that to get the response, Laplace transform y, in terms of this group, the transfer function multiplied by the input. The transfer function has all these parameters in it, kp, tau, zeta, and grouped together, that's the transfer function. Before we look at it in detail, we can start to see what the behaviour of a system is going to be by looking at the relative magnitude of these things. So let's look at the lecture notes again. We've got to this point where we've identified and found the Laplace transform for the transfer function, and here are a few comments on it which we will look at. So first of all, we can see the three terms on the bottom. So what does it mean, the damping factor? Well, its name describes what it does. The damping factor will dampen the response of a system to a perturbation. So the higher the damping factor, the more the response is smoothed out, made even. The lower the damping factor, the more the response is oscillatory and has overshoot. So we can see that if the damping factor zeta is a big number, if it's large compared to the other parameters, then this term will start to dominate, become bigger than this term. So if this term has a large damping factor, it will be bigger than this term, and so then the transfer function will behave more like the first order system. So with a large damping factor, it becomes more like a first order system, and that means the response is just a smooth, gradual increase or change towards a new steady state value. So the higher the damping factor, the more the system behaves like a first order system. As time increases, the second order effects diminish. So when time increases, we remember from our Laplace transform revision lectures, so if time tends towards infinity, we saw that s tends towards 0. And so if s is tending towards 0, this term will start to become negligible again. S squared will become negligible. And so again, it will become more like a first order response. So at short times, the second order effects might be significant, but as time progresses, they will diminish and the response again will become more like a first order response. So the third point is that second order dynamics show differences when the second order effects, the tau squared, s squared, are comparable or larger than the first order effect. So if you have a transfer function where this term is large relatively, then of course that means we're going to have more second order effects in our process. And so that's going to occur when zeta is small. So for small damping factors, there are more second order effects. So how does that correspond to what we know already? Let's look at our response to a step change. So for a unit step change, we have 1 over s is our Laplace transform of the input, and so our output is going to be kp divided by s multiplied by this term tau squared s squared plus 2 zeta tau s plus 1. And we saw previously that to analyze a system like this, we want to find out what the roots of the denominator are, and we would do the partial fraction expansion after we'd found the roots. Another term for the roots is poles. In control, we talk about poles and zeros. Zeros are points at which the numerator is equal to 0, and poles are points at which the denominator equals 0, and so that's when the response tends to infinity. So at 0 the response tends to 0, at a pole the response tends to infinity. So the poles correspond to the roots of this equation which we found before. And we can relate the behaviour of a system to what these poles are. So for the second order system, we see that it can be written out as s minus p1 multiplied by s minus p2, and we'll see that p1 and p2 are a pair of complex conjugates. Zeta over tau plus zeta squared minus 1 over tau. p2 is minus zeta over tau minus zeta squared minus 1 over tau. Now if zeta is greater than 1, then zeta squared is greater than 1, and this value here is greater than 1 minus 1, so this is a positive number, a real number, when you take the square root. So if the damping factor zeta is greater than 1, you have two distinct real poles. If the damping factor is equal to 1, then zeta squared minus 1 is 0, and so then you have two equal poles. And if the damping factor is less than 1, then this becomes a complex number and you have a pair of conjugate poles. So there are three distinct scenarios which will affect the behaviour of the system. And we can see how the system responds accordingly. So if the system is if the system has damping factors which are greater than 1, and so that's this case here, we call it overdamped. So that means that the damping factor is dominating the response, and it has a slow response and it slowly approaches the steady state value. If the damping factor is equal to 1, we call it a critically damped system, and that will mean that the system responds and approaches the steady state value. Critical damping, there's no overshoot, and it will approach the system. If the damping factor is any smaller than 1, then it's called underdamped. So underdamped is smaller than 1, and as soon as it becomes smaller than 1, then there will be some overshoot in the response. So here we have a response for an underdamped system. The response increases quite quickly, but then there's overshoot, and then it oscillates and decays towards the steady state value. So the fastest you can get to the steady state value without overshoot is for a critically damped system where damping factors equal 1. If you want to get to the steady state value faster, you can do it with an underdamped system, but then you'll have overshoot and it will oscillate above and below the steady state factor, the steady state value. So we can look at this for our example. So we take this again, and I took a protractor and I put the bopper aligned up over it and gave it a kick, and it oscillates back and forth, and I measured the angle against time to see how it responded. So this is a system. It would be quite complicated to try and work out the equations which determine what's happening here. There's quite a few factors involved, but it's easy enough to measure those things. So measuring those things, we get this response. So this is time, and this is on the y-axis, it's the angle. 0 was in the middle, and I had it oscillating, starting below 0, and then it would oscillate above 0 and back and forth and so on against time. And all of this happened, that's 1 second there, so it's oscillating back and forth more than 3 times in 1 second. And there are a few characteristic features of a response like this. We can see that there's an overshoot, A, on the first cycle, and there's an overshoot on the second cycle and on the third cycle, and so on. We know 0 is going to be the steady state value because I put that in the middle of the position that it can be in. And here we can see that there's a period to this oscillation. It goes up, it goes down, and then it starts to go up again, so that's one complete period. So you could say that that's 2 pi radians for that period of time. So with that, we can start to do some analysis. Just as we did for the first order case, we can do it for the second order case too. So you can find equations for this. We won't derive them, but you can find them, and you will know that we have a thing called the overshoot. So the overshoot is defined as the ratio of A over B. So B was the initial displacement, and then A is the overshoot beyond the steady state value 0. And it can be shown that the overshoot is equal to the exponential of minus pi times zeta divided by the square root of 1 minus zeta squared. We can measure A and we can measure B from the response. A is about 33 degrees, B was about 36 degrees. And so we can use that to find what the damping factor is. Damping factor was equal to 0.028. So that corresponds to less than 1, and so that's an underdamped system. And of course that makes sense. Underdamped, this has a significant second order oscillatory response to the perturbation. So we'd expect a low number for that. Similarly, we could work that out from the decay ratio. This peak is getting smaller over time. So if you take the ratio of C to A, of one peak to the previous peak, that can be shown to be equal to the overshoot squared. So that's another way of calculating the damping factor. Okay, and then the other parameter is tau that we might want to find. And so we have the radian frequency. So the frequency is the number of degrees in one period, 2 pi, divided by the time it takes for one period, which is this time here, which is about 0.27 seconds. So pi divided by 0.27 seconds gives us radians per second, which is the radian frequency of the response. And it can be shown that the radian frequency is equal to 1 minus zeta squared, square rooted, divided by tau. We found a value for zeta, and so we can input that to find a value for tau, and we get 23 seconds. So in this case, with a very small value of damping factor, essentially tau is equal to the inverse of the period, as this term is about equal to 1. So, in summary, characteristics of the underdamped system. The underdamped response, it's initially faster than the critically damped or overdamped, which are in turn sluggish. It oscillates with progressively decreasing amplitude, and the oscillatory behaviour becomes more pronounced with smaller values of damping factor. Okay, thank you. The next lecture is going to look at an engineering application of this for process engineering, which is the jacketed reactor. Thanks very much, and see the next lecture.